Alright, we've started to record. I'm just going to share my screen. Here we go. Can everyone see my screen? Awesome, nice. Okay, so I'm going to be covering undecidability. So that's going to be with regards to, zoom in a bit if you can, okay. Is that better? Perfect, awesome. So yeah, I'm going to be covering undecidability. So that's going to cover the two handouts that we did. So the first handout talked about the halting problem and the proof of the halting problem as well. So I'm just going to go through all of that just to sort of give you guys an idea on how the halting problem works. And then we're going to talk about undecidability via reduction, so reducing the halting problem to another problem, and also semantic and non-semanticness with regards to Rice's theorem as well. So yeah. Okay, let's get started then. So, halting problem. Does anyone know what the halting problem is? If you just type it, a quick definition in the chat. A program that shows if another program would halt or hold. Yep, that's it, good. When you reduce the halting problem to something to prove undecidability. You can use a halting problem to prove undecidability, but what I'm asking is for the definition. But yeah, as Darko said, the halting problem is a program that will take input from another program of its code and see if it will halt or hang, or halt or hold, for example. I'd probably say hang just because it's the definition used in the handout. So if I just write that down, so a program that takes input of another program and assesses if it will halt or hang. So that's the halting problem. So yeah, the halting problem will do that. And as you already know, we know that it's undecidable. And it's a undecidable decision problem. And now what we can do is we can actually prove that. So for example, I'm just going to show you how to prove the undecidability of the halting problem now. So for example, let's say, like we were doing yesterday, we are going to assume that the halting problem is regular. I mean, not is regular, sorry, is decidable. Yeah, we're not doing DFAs or languages. We're doing the decidability. So we assume the halting problem is decidable. So essentially, we should have, if I do this, this means that we have public void, well, public boolean halting string code, and this will return if a program is going to halt or hang. If you input the HP to itself and condition that if it halts, it will just loop and not return anything, and if it hangs, then return the whole program just contradicts its meaning. Yeah, basically that's what the proof is. So yeah, we've assumed that this halting problem is decidable. So we have this sort of code here that will take in another piece of code and return if a program is going to halt or hang. And we also have another program which will just do the opposite of itself. So we have a public void opposite. So it will take an input, and if the program that it takes in will hang, then we don't hang, and we halt. So if I just write this down, if this code hangs, then we halt, else we hang. So essentially it just does the opposite of whatever we put in this code, right? And so if we put the halting problem into this opposite function, then if we do that, then it should enter an infinite loop, as Darko said, because if it halts on itself, so if we, actually what I'll do is I'll put this down here. If we put in the halting function into the opposite function, we have either two outputs. If the halting problem hangs, then we return and slash halt. If the halting problem will halt, then we hang. And this halting problem, because obviously we've defined what we've put into the opposite function, this halting problem will contain the opposite function. So essentially it's like doing this. So let's say we have our public static void main string args, you know, as like a Java program, right? And let's say we've called halting on the opposite, but also the opposite on the halting as well. So basically this is what we're doing. The halting problem takes in the opposite, but we also have the opposite that takes in the halting problem. So when we do this, if the opposite will hang, then the halting problem decides that it's going to hang, but then the opposite is actually going to do the opposite of what we've just done. It sounds a bit confusing, but essentially, because obviously we know that the halting problem determines if a program's going to hang or not. So whatever this does, surely this should be the same, but it's not. And so because of that, we will enter that infinite loop as such. Hopefully that does make sense. And then yeah, so whenever we have that, that means that our halting problem contradicts what we input, i.e. the opposite function will not hang if the halting problem has decided that it will, and hence due to this contradiction, the halting problem is undecidable, because although we could, for example, take in like a simple function like system.exit, which is just a thing in Java that will just cause it to terminate. We could take this out and we'd know obviously that it will hang, but it's not going to do that for all things. It's not going to use that for all things. So that's essentially how the halting problem works. How we prove that it's undecidable, because it's a contradiction. We don't have that. We don't have it such that all problems can be predicted as such. How do we use the halting problem and reduce it to solve a problem? Yeah, sure. Let me go through that for you. I'm just going to bring up my notes just so I can start with that. So if I scroll down a little bit, just because on the recording last time I could see that I couldn't see the text. Do you use halting to also prove a semantic is undecidable? So to prove if a semantic is undecidable, or if a semantic property is undecidable, yeah, so let me just have a look. Okay. So yeah, you would reduce the halting problem to Rice's theorem in order to produce the property that Rice's theorem is undecidable. Okay. And what I'll do is, firstly, I'm just going to talk about how to reduce a problem to, reduce the halting problem to another problem, just so we can go through Darko's as well. Gotcha, so it reinforces Rice's theorem. Exactly, yeah. So we don't need to sort of explicitly say and state the halting problem all the time. We just need to say by Rice's theorem that it does what it does. So, undecidability by reduction. Okay. I know all the definitions, but I don't know how to actually solving a problem. Yeah, so what I'm going to do is I'm just going to go through a problem from the 2012 paper. And what I can do is show you how I'd approach it, just so we can sort of see what sort of working out I do. So if I copy paste this. Oh wait, no, sorry, it's not from a 2012. It is from the 2022 paper. Okay. And what I'm going to do is I'm going to let you guys have a go as well, then I'll go through the model solution as well. Okay, can you guys see that? Or is it, like, not visible? Yep, awesome, okay. So I'll just read it out for you guys. So we have a program in Java which is said to be purple if it either halts or contains an even number of A's. We need to show that purpleness is undecidable. Does anyone want to come up to the stage and attempt it? Okay. Shay, do you want to come up to the stage then? Cool. Yo.
Okay. Yeah, so programming Java is supposed to be purple if it either halts or contains an even number of A's, show that purpleness is undecidable. So we'd want to reduce the halting problem to the purpleness problem.
Yep.
So assume we have like some black box that can solve the purpleness, or that tells us if given a program it's purple or not.
So we assume that we have some function that will decide if a program demonstrates purpleness or not. Okay.
Yeah, and then what we can do is if we have that program, so we know that the function will return true if the program halts or if it contains an even number of A's. If we make a step at the beginning, like a pre-processing step, which adds an A if it's got an even number of A's, that means, so we make some new program, P prime, which takes the program P and it ensures that it has an odd number of A's. So,
yep, just give me 1 sec.
Yeah, that's right.
So the function will return, if I just scroll down a bit, false if we have a program that hangs and has an odd number of A's.
Oh no, even. Oh right, yeah. Okay. So what we can do is we can say if the program has an even number of A's, let's make a new program from that program by just adding an A at the end so that it has an odd number of A's, just like as a comment or something.
Which will determine if the program we input to the purpleness checker has an even number of A's, and then it will make it such that we only have an odd number of A's. And so we only have one true situation and one false situation. Okay, cool.
Yeah, so that eliminates the possibility. If the function then returns true and it says the program's purple, then there's no way that the program hung and had an even number of A's because it's we made sure it had an odd number of A's, so that and condition won't be met, that'll be false. So if the function returns true, that basically just means the program halted. And if the program then doesn't return true, that means the program must have hung. And so we've managed to make we've managed to make the purpleness black box solve the decidability problem, which we know we can't do because we can't solve the halting problem. And so we have a contradiction, and so the purpleness problem must be undecidable.
Yeah, perfect. So hence we have made a program that, what do you say, a black box?
Yeah, I just called it like a black box, just because we can imagine we have some black box where we feed it an input and it just tells us if it's correct or not, like a source of truth.
That is a black box of a program.
Uh, well, we've made a program using like the black box. Like the assumption we have is we can solve purpleness. So that assumption's like a black box that tells us if something's purple or not.
That is like a black box that tells us if a program is purple or not. And hence we have also solved the halting problem because this program decides whether we halt or hang. This is a reduction from of the halting problem to the purpleness problem. Hence, we know that the because we have a program that can decide the halting problem, we reach a contradiction because we know the halting problem has been proven to be undecidable. So yeah, and hence via reduction we know that the purpleness property is also undecidable. And yeah, that's basically it. So Shay, that was really well done. That was perfect. So yeah, I'll just quickly go through a summary of what we've just talked about then. So yeah, we have firstly, we have firstly that we want to reduce the halting problem to the purpleness problem, in order to show that because the halting problem is undecidable, that the purpleness problem is undecidable as well. So we assume that the purpleness problem is decidable, and then we reduce the purpleness problem down to a function. This isn't reduction as we've defined in the handout. What I mean is that we're just cutting down the purpleness problem so that it's only testing for the halting problem. So, for example, we've taken all these inputs here, all these different situations in which we have the purpleness property return true and return false. So like we said before, a purple program is one that halts or it hangs and it has an even number of A's, but it's false if it hangs and has an odd number of A's. And hence we can make a program to sort of reduce this purpleness property down to the halting property to see if we can halt or not. So we can make a program that pre-processes the program which will determine if the program we input to the purpleness checker has an even number of A's. So essentially, it's like if I make some code just to show you what I'm on about. It's like saying we have this function purpleness, and let's say we have string code. By making the conditions into halt to true and hang to false, we basically convert the purpleness. So it's not a sort of making a halt to true and hang to false. It's more so that we show that the purpleness problem is just a representation of the halting problem by just eliminating this possibility right here. So we're eliminating this possibility of happening, because then we will know that it's purple if it halts, and if it hangs, it must not be purple for all the different possibilities. So it checks before the halting problem. Sorry, it checks before the halting function if there is an even number of A's. If there is, it returns true. Otherwise, it goes through the halting function. No. So if I just write the code down, hold up. So what it would do is we have public void, or it would be public string pre-process string code, and basically what this will do is makes the number of A's odd if it is not already, and then this will check if code is purple or not. And so when we have that public static void, when we run it, for example, let's say we pre-process, let's say we have string code. So we have our code in a string, right, is equal to, you know, the string. And then we do pre-process code, and this will obviously make the number of A's odd if it isn't already. And then we do the purpleness of the code. So if I just do code is equal to that, and then this basically. So we have our code. We replace our code with a code that has an odd number of A's. And so the purpleness function, when it takes in the code, we know that we've eliminated this top possibility here of a program hanging and having an even number of A's, because we know that we will always have an odd number of A's in any possibility. So if it halts, if it halts, then we know that it's purple, but if it hangs, we know that it's not purple because it has an odd number of A's. And this is just basically, we're just saying that it's the same as a halting problem. So like I was saying here, hence we know if the function returns true, we know it can only hang and not have an even number of A's. If it's false, we know it hangs and has an odd number of A's. And just to clarify, the only reason why I've talked about true and false is because I've written out the pseudocode for it, just to make it such that it is like an actual function. So yeah, you'd really need to be explicit when it comes to these types of things, like for example writing out pseudocode for this, or just describing what your verifier of purpleness will do. So this is called reducing the halting problem to purpleness. Yeah, so we reduce the halting problem to purpleness because the halting problem is a subset of the purpleness problem, because the halting problem will check if something hangs or halts. So essentially, let's say we did actually have like the halting function. So if I bring that from the top one, let's say if I did have this halting problem, right? And it will return if a program's going to halt or hang, then if we do this, if halting code, so if it halts, then we know that it's purple. So we return purple. Else, we check the number of A's like that. Obviously, in code you wouldn't be able to do this, but I'm just doing it for the sake of pseudocode. So if I copy paste this, if check number of A's, if we've checked the number of A's and it's equal to 0, and when we modulus it by 2, so this just makes it, this is just checking if it's even using the mod. So if it's even, then obviously we know it's purple, and else we know it's not purple. So essentially, when we do this, we're reducing the halting problem to purpleness because it's like the main property that we check for first. And so when we have the property of purpleness, it contains the halting one. So when we reduce it to purpleness, we're basically saying that the halting problem is the same as purpleness in a way. So is it purple if it both halts and has an even number of A's, or one or the other? So yeah, it's just purple if it halts and has, well, it doesn't really matter if it halts. What we're trying to say is that if it halts, then it's purple. But if it doesn't halt, but it has an even number of A's, then it's purple. But if it has an odd number of A's, then yeah, it's not. So to show any non-trivial semantic property of any program is undecidable, we just non-trivial. Sorry, what's a non-trivial semantic property? I don't understand what you mean by that. Of any program is undecidable, we always just reduce the halting problem to it, and we're good. Yo.
Basically, what I'm saying is like, how like asking, is this undecidable? Yeah, is purpleness undecidable? We only do reductions if we can't apply Rice's theorem.
Yeah, exactly.
Oh. So you can't apply Rice's theorem to... Oh, purpleness is... Wait, what is meant by a semantic property then? So I thought, isn't a semantic property just any property of a program that you can't like get as an output?
No, so a semantic property is one that has its input and output behavior related to the property we are on about. So, for example, if we have a function that will double a number, its input and output is always related, and hence it's semantic. If it's not semantic, then its input-output behavior isn't related to the property. So, for example, I could say a function will take in a piece of code, but we always return 1. That's not semantic because it doesn't relate to whatever. Or for example, math.random doesn't relate to the input. So
semantic property is behavior of code.
Yeah, it's related to the behavior of the code.
So isn't that, what other kind of property is there that's like a not semantic property of code? Like in the purpleness example, what is a non-semantic property?
The halting problem, for example. Actually, wait, no, hold up. A non-semantic property.
Yeah. Halting is a semantic property, no?
So halting. Hold up. Let me just think for a sec. Hold up. Non-semantic property.
Hey, Shay.
Hey.
Yo.
I'm just trying to see. Halting is an example of a non-trivial semantic property. Yeah.
So halting is a semantic property. So that's why you can say like because like Rice's theorem states that every non-trivial semantic property is undecidable.
Yeah.
Halting problem just like complies with Rice's theorem as well.
Yeah.
So can we not just say like why do we need to reduce the halting problem to a problem in order to show that a semantic property is undecidable? Why can't we just say Rice's theorem states that any non-trivial semantic property is undecidable, therefore purpleness is undecidable, as
Because
it's a non-trivial
purpleness isn't a
semantic property.
semantic property.
So what? That's what also I was trying to ask. What is defined as a semantic property, and what would a non-semantic
A
property
semantic property is in regards to the behavior of some code. So it's, for example, what it inputs or what it outputs. Purpleness is about
be? Okay, so semantic is behavior, but then isn't that like everything? Like what else is?
no, because if we're thinking about how many, like for example,
I guess you could
Properties
say, for
of-
example, like the syntacticness of a piece of code is not semantic, for example. Like Shay's just about to put, that's a semantic
Is
property.
that a property?
I mean, yeah, one property of this code is, do we define a variable called a? That doesn't affect the input and output of what this code does. They both have the same behavior, but one of them meets that one of them meets that syntactic property, but one of them doesn't.
Okay. So is purpleness a semantic property?
So purpleness isn't a semantic property, because
How come? No, that's what I don't get.
yeah, because we have the even number of A's or an odd number of A's, but that's in the code, right? But we can always change that, so it's not always related to the input. Oh, wait,
But
hold
the
on.
input is the number of A's and no?
No,
Wait.
it inputs the program.
Yeah. Because we can change the program. Wait, hold up. Is
What? Hold on.
hold up. Is
Um,
the number of A's in a program semantic? I would assume it's semantic if the program is an input, but I don't know. But hold up.
No, because it doesn't necessarily change the behavior of the program. For example, if you add it as a comment,
Yeah, that's true. So I've just clocked. So basically, I think you're thinking about it like this. I think you're thinking about it like if we put in a program to the halting, or I mean to the purpleness checker, and the number of A's differs, then it's purple or not, which is semantic in that point, but the actual program having the number of even or odd A's is not semantic because, for example, if I have like the purpleness, let's say we had the code, right? So our string code is equal to AAA or A, right? For example, so we have these like two different ones. So this is supposed to be an order, but I don't know why it's not. But anyways, so for example, if we had like a comment, like for example, actually, I'm just gonna break it down because this is actually a piece of code. Let's say we have this piece of code right here, like the whole public static void thing, and we can change the number of A's, but it's not going to affect how the program works, and hence it's not semantic because it doesn't affect the input-output behavior because it's a comment rather than something like, I don't know, like math.
So the comment isn't the input. I'm talking about like
No, but the whole point is
purpleness
it
does
it's
depend on the input.
no, but that's the thing though. The purpleness itself is
Isn't that
deciding whether
just
we.
telling you if it's odd or even number of A's?
Sorry, what?
The purpleness is just like if it's like an even number of A's, it's not purple. Odd number of A's, it is purple, right?
Yeah.
So surely that's related to the input because if you input an odd number of A's, it's going to be purple. If you input an even number of A's, it's not purple. Therefore, because it's a property that's dependent on the input, therefore it's a semantic property. Because the behavior is affected by the input. It's not. It's definitely not a syntactic property.
no,
Like-
because
No, but-
the input is not the I forgot what I was gonna say.
I think what Shay was about to say is that because we're not really checking for if the number of A's has an effect on purpleness, we're trying to check about the number of A's itself rather than anything. Because the only thing we care about in purpleness is that if it hangs or not, right? And after that, we care about the A's, right?
Oh, so the first thing you're trying to see is if it hangs.
Yeah, because if it hangs, we know it's purple, right?
Yes.
Yeah, and then if it's not, then we check the number of
Okay,
A's.
right.
But
That makes sense.
that the number of A's will not affect if that program will hang or not, and hence it's not semantic. Because, for
Okay.
example, like I said before, system.exit, I could literally put this and I could say AA, but I could also say AAA in like this code here. And this is odd, this is even, but I know I'm still going to terminate. So it doesn't really affect the input if it's halting. If it was just a check of if there was an even number of A's in the code that affected the program, then it's semantic. But like we say, a comment, for example, is contradicting to this because we have the comments which affect for a number of A's, but it doesn't affect the program itself. And this program is an input to the purpleness, after which we
Oh, sorry. Okay, I think I misunderstood what you meant by the purple. The
yeah
program is the input,
yeah the program's the input.
Yeah.
not the number, not like a string of A's.
No,
No. The whole like just the
yeah,
program.
like this is a
You're
piece of
inputting
code
this
we can input.
this program. You're actually inputting the code into the
Yeah.
purpleness function.
Yeah.
So what's the purpleness function then?
So
Where
the
is that?
purpleness function will check if it halts or not, and then if it doesn't halt, then it will check the number of A's. And if the program hangs and there's an even number of A's, then it will return true. If not, it will return false. But that doesn't just depend on like the actual functional code. It depends on the comments as well, because this whole thing that I've just highlighted here is like the string that we input to the purpleness function. Stupid question, but what is orangeness, purpleness? Or are they just definitions? Yeah, they're just random names. It's just like a property. Like I could say that yap is a property in which a person will continuously speaking until they like. We could say that yap is a property in which a function will continue to print, and it will hence hang. And so essentially we could say that the property of yap is undecidable because we can't decide the halting problem. And if we had a program that could decide yap, we could have a program that decides the halting problem, and hence we reduce the halting problem to it like that.
Yeah.
Okay, right. Makes sense. Okay, thanks, guys.
Cool, awesome. So yeah, that's essentially like how we go through it there. What's the property of orangeness?
Oh, one more thing. Are you gonna put this on like these notes, this like notes that you've made on how to do the reduction? Can you put
Yeah.
it on like something?
Yeah, I'll put in the recaps.
Cool.
Awesome. Okay. Good talk. I love that. Okay, back to what we were talking about. So obviously we've just proved how to do the undecidability by reduction, right? So that's just by reducing the halting problem to another problem in which we want to show that it's undecidable. However, we can also have like, it doesn't always have to be the halting problem. If you know that there's another problem that's undecidable, you can reduce it to that. Obviously in the exam they're not going to ask you, but yeah. So for non-semantic properties, we reduce the halting problem to it, and for semantic problems, we use Rice's theorem. Yep, exactly. Because for semantic problems, we've already proved Rice's theorem, and because we've already proved Rice's theorem, then we don't need to sort of go over that proof again. So we can just say via Rice's, so and so, you know. But yeah, I can give a property or an example, sorry, using Rice's. So if I just scroll down a little bit more. Okay. Oh, there we go. So Rice's theorem. Does anyone know what Rice's theorem is, by the way? If you just pop that in the chat. any semantic property of code that holds in some case and fails in another case is undecidable. Perfect. Well done. So yeah, Rice's theorem is that if a property is semantic and fails to hold in some case and can hold in some case, it must be undecidable. And now we've already proved this via the halting problem. What I'll do is I'll just put the proof of the halting problem on here. Hold up. If I just have a look. So I'm just going to try to explain this then. If I do get it wrong, just correct me. But yeah, so to prove Rice's theorem, we use the same method we've done before, i.e. the halting problem, reduction to another type of problem. So for example, we can say, if we consider a function that is polite when it only prints polite words, now we know that this is semantic because if it has an output that prints polite words, then its meaning is related to the property itself. So, for example, we could have this, right? Zoom in, yeah, sure. Is that cool? Awesome. So yeah, we could have this code here while true, which is polite because it's not printing like bad words, like it's not printing swear words. However, if we print out like a bad word, for example, it's not. And so, for example, here we can prove that if the politeness property will hang, but a property in which we print out like a swear word, for example, will halt, then we can sort of reduce the halting problem down. Because, for example, p halts if the code is not polite, for example. Does that make sense? Or does anyone have any questions regarding that? Okay, I'm going to assume that there is no questions. All good? Okay, cool. Awesome. I'm going to move on to the next part then. Okay, I'm just going to skip this just in regards to time, so I'll just delete that. But from this, you should be able to sort of see how a semantic property can hold and not hold in both cases. So, for example, we had this and that. So what's the difference between the halting problem and Rice's theorem? So that would be an invalid question. You can't sort of have a difference between the halting problem and the Rice's theorem. The halting problem is a problem that decides whether we have a program that can halt or not, whereas Rice's theorem is a theorem that tells us that any semantic property that can hold in some case and not hold in another case is undecidable, and we've proven this via the halting problem. So yeah, hopefully that makes sense. Okay. And then obviously, now we know Rice's theorem. Just to reiterate, obviously, Rice's theorem, if a property is semantic and fails to hold in some case, and can hold in some case, it must be undecidable. So, for example, when we do like a question, for example, if I take out, if I zoom in, let's see. Let's have a look. Bro, just try to pause the live, bruh. But yeah, so we have this question here. Now, what I want you guys to do is what we've sort of done up until now. Just see if you can answer this, and then I'll go through it as well. So we have the body of the code, which is a function that will return a natural number, and it takes in a natural number, and it's sleepy. So the property is sleepy of a program when we have the input of 5, 6, and 7, and they all return even numbers. So yeah, if you want to have a look at the answers and just out of the answers, choose one and just put your reasoning down in the chat, and then we'll discuss that in a moment. Okay, so we have one vote for C. Is it B because it sometimes holds and sometimes doesn't? B since it's a semantic property but it's undecidable due to Rice's theorem. Yeah, so yeah, it's B. And I'll explain why. So we'll go through each one and I'll just show how we can sort of eliminate the other answers. So essentially, the whole point of sleepiness is that when we input 5, 6, or 7, it will return, all of these will return even numbers. So essentially what we're saying is that the input is dependent on this. So if we input 5, 6, or 7, it will have some property in which the output is affected. So hence, because the input and output behavior is related to the meaning of the property or the semanticness, hence it's semantic. So in that sort of area then, C and D have been removed because we know it's semantic. And then that leaves us with A and B. So sleepiness is semantic and decidable, and semantic and undecidable. How did you know it's semantic? Because if you look here, if you look at the input, it relates to the property. So if we input 5, 6, and 7, and the output for all of these return even numbers, then we know that the input is related to the meaning, and hence a sleepy piece of code will always be related to its meaning, and hence it's semantic. If the input was a string, for example, it would not be semantic, right? No, it would still be semantic. Because, for example, let's say we had f of like x, for example, and for example we had a function that takes in a string and returns if it's even or odd, returns an even, well, it'll return even numbers if the string has an even length, right? So if our string has an even length, so for example xx, you would have it such that the function will return even numbers, whereas if we had xxx, for example, it won't return even numbers, and hence that if we change the property of sleepiness, it would be the same thing. So because it is related to its input, it doesn't really matter what type of input we have, as long as the input's related to the output, then it's still semantic. Awesome. Okay. And then obviously we can have different ways in which we have the output with respect to 5, 6, and 7. So for example, let's just take f of 5, and we can say that f of 5 returns 5, right? Now this is a contradiction to the sleepiness property, but we can also have f of 5 returns 2, right? So obviously the code isn't defined here, so essentially we could say that any piece of code can hold, for example. So we essentially just define the code by ourselves, and we can say, oh, this is sleepy and this isn't sleepy. And now because we know it's semantic and we know that it can hold and not hold in any case, that means that it is, by Rice's theorem, which we've just discussed, is undecidable, and hence the answer is B. Does that make sense? I don't understand. It's not decidable. It's undecidable. You don't understand how it's undecidable. Okay. So essentially, because we know Rice's theorem, right? Do you get how Rice's theorem works? Like, yeah. So because we know that the property sleepiness can hold in a case and cannot hold in a case, so we can have a function of 5 that returns all even numbers, and we can have f of 5 that returns odd numbers. Because we can have these two properties, it can hold. So we can have sleepiness works with this function. So this is a sleepy function. However, we can't have this. This isn't a sleepy function. And so this holds, if I can spell holds correctly, and this doesn't hold. And hence, because we've proven that there's a case in which it holds and doesn't hold, by Rice's theorem, which I'll just copy paste down here, if a property is semantic, which we've already sort of proved, and it fails to hold in some case and can hold in some case, it must be undecidable, and we've proven that it can hold in some case and it can't hold in some case, and hence it's undecidable. Since there isn't a specific structure, you can decide what's in the body of the code. Yeah, exactly. You don't really need to specify it though. You could just say, let's say we have f of 5 that returns this and f of 5 that doesn't return this, and so it's so we'll hold in both cases. So yeah. For example, in this case, we haven't had anything here. But like, let's say, for example, if they've defined it, you would need to be able to know if the output is related to the input, and hence, based upon that, you can check if it's semantic or not. And hence, if it's undecidable or not. Okay, nice. That's awesome. And then, yeah, that's basically it for undecidability. So, undecidability... how do you know if it's going to be even or not if you don't have the code? Because you don't need to have the code, you can just theorize. So I can say that, let us say that f of n will return double, right? And if it returns double, then it's even, right? Oh, no, wait, never mind, that's why it's undecided. Exactly, yeah, that's it. Because there can be an infinite amount of possibilities in which we can have a function that will return even numbers, and we can have an infinite amount of possibilities in which a function can return odd numbers. Because literally, we can have a function, like, for example, even, that has this, and it will return an even number. But we can also have another one that has this as well. And literally, we can do this until eternity, and that is a function that's even. But we can also do the same thing for an odd one, and hence it will always be undecidable because we have to check for an infinite amount of different methods, obviously. And also, Rice's theorem states that as well, because we've obviously reduced the halting problem to Rice's theorem. But yeah. Yeah, exactly. F of phi can equal pi if you want it. Exactly, yeah. Awesome. Yeah, def f num is equal to return high. Nice. But yeah, that's basically in terms of undecidability. Does anyone have any other questions in regards to that? Doesn't that make everything undecidable? No. We could have something that's decidable, in which it will hold in all cases. So for example, I could literally have a function that will always return true. Now this function will be decidable because it will hold in all cases. The only reason why it won't be undecidable is if it can hold and not hold in other cases. It's just for this specific example, where we haven't given an implementation, as Fred says, where it's not going to work. Yeah. How do you check if a non-semantic property is undecidable? You have to reduce halting the halting problem to a non-semantic property in order to check that. If it returns something, it's sleepy, for example, that will always hold. Right? Yeah, exactly. Well, actually, no. Because for it to return, it would have to be... Actually, wait, hold up. If it halts, then it's sleepy. If it's gonna hang, then it's not sleepy. I think so. I would assume so, yeah. Because if it hangs and if it halts, it doesn't necessarily always relate to the input and output behavior, and hence it's not semantic. But if we have a function that will always return, and it's sleepy, then we know that it holds in all cases. So if it will always return and we know it's always going to return, for example, function return true, then this is semantic. But yeah, and hence we know it's decidable. Exactly. Non-semantic reduce halting semantic rice. Yeah, that's exactly perfect. I could eat some rice now. But yeah, any more questions? You can't forget the two exceptions for rice. Exactly, yeah. You want to make sure that you do state rice is firm before you actually say anything. So if it's semantic and it fails to hold in some case and can hold in some case, then it must be undecidable. So it has to hold and not hold in two different cases that you can just say, for example. Like, for example, this for the question above. But yeah. If there aren't any questions then, I think that's it from me. Once again, thank you guys for listening. Really appreciate it. But yeah. I'm just going to stop recording now.